Next unit of lessons is on sequences and series. A sequence is a list of numbers, and we call each of those numbers terms. Okay, so a sequence is just a list of numbers. We call each of those numbers terms. A sequence is defined by a function, so there's some sort of a rule that will give us these terms. And the way we create a sequence is by plugging in consecutive integers to the rule. So we start by plugging in 1, and then plug in 2, and then plug in 3, and plug in 4, and that gives us the terms of our sequence. A finite sequence is a sequence that has an end, and an infinite sequence is a sequence that goes on forever. So our first type of question wants us to find the first 6 terms of this particular sequence. So that function is our rule. The notation, the a sub n, we say that that font is known as a subscript when it's a little bit lower and smaller than the regular font. So a sub n tells us which term it is. So we start by saying a sub 1 means the first term of the sequence. And the way we find the first term of the sequence is by plugging 1 into the rule. So that gives 5. So our first number of this sequence would be 5. To find the second number, or a sub 2, we plug 2 in to the rule, and we get 7. To find our third, plug in 3, and we find 9. After plugging in 3 values, if you believe you see a pattern, it is okay, most likely, to continue with that pattern. In general, 3 terms following a particular pattern, it's pretty safe that that actually is the pattern. I would not assume a pattern after just 2 values, because there's a lot of ways to get from 5 to 7. We could add something, we could multiply by something. There's a lot of other things that could be happening there. But if it works for 3 numbers, you can safely assume that it's probably going to continue. If you don't notice a pattern, then you just keep on plugging in numbers. So if you notice, okay, 5, 7, 9, looks like I'm getting the odds, then you can just keep on writing odds up till the 6th one. If you don't notice a pattern, you just keep on plugging in numbers. So you'd plug in 4, plug in 5, plug in 6, and that should give you those values as well.
Will it ever be more than one thing? Will it be like plus 3 times 2?
We can have complicated rules. Our rules aren't going to get really complicated. But yeah, they can get pretty tricky in coming up with exactly what the pattern is. So then that's the case if you just don't see exactly what the pattern is, then you just keep on plugging in numbers. The second question asks for the same thing, the first 6 terms, but the notation is different. It uses the f, the function notation. You find the answers in the same way. You begin by plugging in 1. Plugging in a 1 for n gives an exponent of 1 minus 1, or 0. Negative 2 to the 0 power is 1. Anything to the 0 power is 1. Then we plug in a 2. We give an exponent of 1. So it gives negative 2. Plug in a 3. 3 minus 1 is 2. Negative 2 squared is positive 4. And after 3 terms, if you believe you see a pattern, it is safe to continue it. So how could I get from 1 to negative 2 to positive 4? Multiply by negative 2. So that means my next value would be negative 8, and then positive 16, and then negative 32. And if you see that pattern after 3 terms, it's fine to continue with it. If you don't see it, then you just keep on plugging in the numbers. Plug in 4, plug in 5, plug in 6, and that will work just as well. Maybe not as quick, but it will work as well. Questions? The next 2 examples are of the same type, so go ahead and try the next 2 examples. Okay, so starting by plugging in 1 gives us our first term, which would give 4. Plugging in 2 gives 3. Plugging in 3 gives 2. And our sequence is just counting down. So we can continue counting down until we get to our 6th answer, a -1. Okay, and the sequence is the whole list of numbers. It's not just like that final number is our answer. The answer is all 6 of the values, the 6 terms. For the next one, 5 to the first is 5. Getting ahead of myself. 5 squared is 25. Plugging in 3 would give 125. Plugging in 4 would give 625. Plugging in 5 would give 3125. And plugging in 6 would give 15625. Okay. Questions? In the next group of questions, we're asked to do a few things. To describe the pattern, so we're going to talk about in words kind of what do we see happening here. Then we're going to use that pattern to the next term should be. And then we want to write a rule for the nth term, which means that if I wanted to know what the 100th term was, I could just plug 100 into that rule and get the answer, instead of having to find every term along the way until that term. So first, describe the pattern. What's happening here?
It's passing by 1/3.
Negative.
It's getting 3 times.
Okay, so we've got a positive negative flip going on, and the bottoms are multiplying by 3, or we could say the whole thing is multiplying by 1/3. So what would the next term be?
1 over 81 times 3.
Okay, 81 times 3, which is 243, and we need that term to be negative because that positive negative flip is happening every other. So now to come up with a rule for this thing. Well, the top is always 1 no matter what, so I can just start by writing that.
1 over 3.
What do we call it when we multiply by the same thing over and over? Like if I do 3 times 3 times 3 times 3, what's a faster way of writing that?
3 to 4.
3 to the power of 4. So you might want to write yourself a little note. When your sequence pattern is multiplication, your rule is going to be a power exponential rule. Because that's what a power is multiplying by the same thing over and over and over. So what we're multiplying by here each time is what on the bottom?
1 over 3.
It's not just a 3.
Negative.
We're multiplying by a -3. And that's what's giving us that positive negative flip. And then we could double check if this rule works. If I plug in 1, do I get the first number in the list? If I plug in 3, do I get the third number in the list? If I plug in 4, do I get the fourth number in the list? And plugging in values of n should recreate that sequence for us. So anytime that your rule is that your sequence, our pattern, is that we're multiplying by the same thing each time, the rule is going to have an exponent in there.
Could it be negative 1 over 3?
If the negative was with the 1, then every single one of these would be negative.
Yeah.
So that negative needs to be included in with the power part.
We usually describe the pattern.
I didn't write it in words, but we just kind of talked about how we were having the positive negative flip and the bottoms were multiplying by 3. In the homework, I don't think it does ask you to describe it in words. I think it just asks you for the next term and the rule. So in this one, what's going on here? How do I get from 2 to 6 and then to 12 and then to 20 in some kind of a logical manner?
I can explain it in my own head, but like you go 2, 3, 4, 5, 6, that's 4, and then 6, 7, 8, 9, 10, 11, 12, that's 6, and then you go up 8, and then you go up 10.
Okay, so the difference between the numbers is 4 and then 6 and then 8, and so it seems like that next difference should be 10, which would give us a value of 30. And that's a really good pattern for those numbers. It's totally true, and it worked for us to be able to find the next one. The problem is with this rule, in terms of coming up with a rule with an n in it, is it's not consistent in that it's not doing exactly the same thing each time. So it totally works for finding the next term. It's just going to be a bit of a struggle coming up with the nth term rule for this.
Can you say that it's, I don't know, it's like something minus n, and then n is only even?
We can't limit what n is. N has to count up every integer value. So n has to be 1, it has to be 2, it has to be 3. So what we're going to do is begin by kind of assigning their n values. This is n is 1, this is 2, n is 3, and n is 4. One strategy that we can use when the pattern is not the same every time. So how that happened this time where it was like, there's definitely a pattern, but it wasn't exactly the same thing each time. One strategy we can try is breaking down the numbers into something that would multiply to be those numbers. So 2 could be 1 times 2. 6, 3. 12 could be a few different things, but kind of looking at what we've already done, what could 12 be? 3 times 4. And what could 20 be? 4 times 5. And then the one we came up with would be 5 times 6. So it looks like there's something good going on there. So now what we're going to do is compare each part of this to the n value. So the first numbers, 1, 2, 3, and 4, how do those compare to n? They are n, right? Like the first number just is n. So the first number in each one of those that I underline in blue is the same as its place in line. So that's going to be the first part of our rule. It's just n. Time. The second numbers are 1 bigger than that. So in math we say 1 bigger as plus 1. So n times n plus 1 is going to be a rule that could give us any term in this sequence. So if I wanted to know what the 100th term was, I could just do 100 times 101 and figure that out without having to figure out every single answer along the way. Okay. So this is one of the trickiest ones. We're going to have a couple tricky patterns to come up with here, and we'll work on the strategies together. Most of them are going to follow a couple of general rules. The last one, where we're multiplying by the same thing every time, is going to be a big thing for us. And there's one other thing that's going to happen a lot for us. So in this one, describe the pattern.
It's 2 over 5 to the power.
Okay, it's 2 over, and then the bottoms are all powers of 5, which we might recognize because over in question number 4, we created a list of the powers of 5, right? So kind of just saw these numbers. So what would the next one be? The next power of 5 is 3125. And the tops are all 2s. So coming up with our rule, the tops are all 2s. And we said when we're multiplying by the same thing every time, so the bottom is multiplying by 5 over and over and over, multiplying by the same thing over and over and over becomes an exponent in the rule. So then I could plug in a 4 for n and get 2 over 625. Or I could plug in a 20 for n and find out what the 20th term is without having to figure out everything all the way there. What's happening here?
It's just an even or an odd.
It's all the odd numbers, or we could say to get from one to the next we are adding 2.
For the fraction ones, does it basically just work every time to take the first denominator of the fraction, or basically like just the first whole fraction with the exponent?
If we are multiplying by the same thing each time, so if that's the rule, then that'll work. But sometimes we're going to have fractions there, and the rule isn't a multiplication rule. But if it is a multiplication rule, then we can just take that first fraction and apply the power to it. Yeah. All right, so on this one, we're adding 2 each time, so what comes next? 11. Okay, when we are adding the same thing over and over and over, so like 2 plus 2 plus 2 plus 2, What's a faster way of writing that? 2 times 4, the number of times it showed up, right? So when your sequence is adding or subtracting, because subtracting is really just adding a negative, your rule is multiplication. So I said there's going to be 2 popular ones we're going to do a lot of, and that's where we're multiplying by the same thing every time, or where we're adding the same thing every time. It's going to be another popular sequence for us. So we were adding 2 each time. So I can do a multiplication 2 times n. Does that work? If n is 1, do I get 3? No. So now I need to do some adjusting. How do I adjust it so that I do get 3? I could try adding 1. Then we need to confirm, did that just fix the first one, or did that fix everything? So like if I plug in a 4, do I get 9? Yeah. So that fixed the whole sequence. So when you are adding the same thing every time, your rule is going to be a multiplication, but you might need to add or subtract something to adjust the starting point so that they match what the terms are. Questions? Coming up with rules is definitely something that takes some practice to get comfortable with. A series is where we take a sequence, which is just a list of terms that have commas, and instead of just making it a list of terms with commas, add them all up. Okay, so a series is when we take the sequence and add up all the numbers that we get. This notation with the kind of strange-looking E thing, the book calls summation notation. Summation means sum or adding up. That's what a series is. I call it sigma notation because that is the Greek capital letter sigma. So I just call it by the letter name. So you just need to recognize what either one of those terms are. So I'll probably say sigma, but the book will say summation. I is the index or the variable involved. So when you see that I, it doesn't mean the imaginary number I. Don't know why they choose to use I, because that is kind of confusing. I already has a meaning. I usually use n's instead, but it doesn't really matter. Whatever letter we use in there is fine. The bottom, it says, is the lower limit, which means that it is the starting place. So the bottom is where we start, and the top is the upper limit, or where we end. Inside of that is our rule, like we were just coming up with rules. So our first question asks us to write this in the summation or sigma notation. So we have to write out our little sigma thing. Don't worry about having it be beautiful. Mine get worse as these lessons go on. They will become very scribbly. At the bottom, we define our variable and our starting place. I like to use the letter N, but you can really use any letter you want. And I like to start at 1. But technically, we could start anywhere. I just find it's usually easiest to start at 1. Inside needs to be the rule that would create these numbers. So when we look at those numbers, 5, 10, 15, what are we doing each time? Adding 5. So when we add over and over, what kind of a rule is that? Multiplication. So we start with 5n. Do we need to adjust, or will that work for us? That'll work. If I plug in 1, I get 5. If I plug in 2, I get 10. If I plug in 3, I get 15. At the top needs to go where we end, but it has to be the n value that would create the end of this. So we end at the number 100. Plugging in what would give us 100? 20. So 20 is what goes on the top, not 100. The top number is not the last value of the series. It's the n that would give you that value. So plugging in 20 would give us that 100. Questions? All right, so we're going to make our sigma notation. So again, I like to start at 1, but you don't have to. There is no clear thing that's happening, same thing every time here. To get from 1/2 to 2/3 to 3/4, we're not multiplying by the same thing or adding the same thing each time. So then sometimes what is helpful is to think of the top and the bottom as being separate things and compare them to their place in line. So how does the top of the fraction compare to the end value? It is in. How does the bottom of the fraction compare to the end value? It is 1 bigger. Where does this series end? It doesn't. There's no end to this. It says plus dot, 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 and that's it. So at the top of this goes an infinity. To say that this is an infinite series, it never ends. Okay? Questions? All right, so I'll start this thing at 1 again. What are we doing term to term? 4 to 8 to 12. We're adding 4, so our rule is going to be multiplication by 4. Do we need to adjust? No. That's fine the way it is. Plugging in 1, 2, 3 gives us the right numbers. What number do we need to plug in to get 100? 25. Last one of this type. Once again, it doesn't look like there's any clear cut doing exactly the same thing each time, adding something, multiplying by something to get from term to term. So I'm going to write that 2 as a fraction, so everything is a fraction, and then do like we did on the second example, where we're going to compare the top and the bottom to their place in line. So how does the top compare to the end value? It's 1 bigger. How do the bottoms compare to the end values?
It's 1 squared, 2 squared, 3 squared.
They are the end values squared. 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, so the bottom end value squared. And where does this one end?
Nowhere.
It does not end, so we put an infinity at the top. Okay. Questions? The last problem, the last type of problem, asks us to actually find the sum of the series. So what we are going to do here is, using the sigma notation, create the terms and then add them up. A series is a sum, so we will need to add the terms that we get. You start by plugging the bottom into the rule. So if I plug in I is 1, I get 2. Then I plug in 2. If I plug in 2, I get 4. Then I plug in 3, and I get 6. So on and so forth. How do I know when to stop? When you plug in 6. When you plug in 6, oops, I changed to ends. I like ends better. But when you plug in 6, you're done. Okay? So the top number does not tell you the number to stop at. So I didn't stop when I got to 6 as an answer. I stop when I get to 6. Then we need to add it up. A series is a sum, so we are going to add up those numbers, and we get 42. So on the next one, what do I start plugging in? 3. We've been starting at 1 a lot because it's kind of an easy place to start, but you start at whatever the bottom tells you to start at. So this question tells us to start at 3. So I start by plugging in 3. 2 plus 3 squared is 11. Then I plug in 4. 2 plus 4 squared gives 18. Then I plug in 5. 2 plus 5 squared is 27. Then I plug in 6, and I get 38, and then I'm done, because we stop when we plug in the top number. Then we add this up. I don't know what that is. We get 94. Questions? Go ahead and try the last two. All right, so on this one, we start by plugging in 5 because that's the number at the bottom. So when I plug in 5, I get 26. Plug in 6, I get 37. Plug in 7, I get 50. Plug in 8, I get 65. Plug in 9, I get 82. Plug in 10, I get 101, and that's where I stop. I stop when I plug in the top number. So then I add that all up. 26, 37, 50, 65, 82, and 101 gives us a sum of 361. Okay. Questions? And for the final one, I start by plugging in 1 because that's what's on the bottom. So when I plug in 1, I get 1. When I plug in 2, I get 7. When I plug in 3, I get 17. When I plug in 4, I get 31. When I plug in 5, I get 49. And add those up. It gives me a total of 105 for that series. Questions?
All right, I don't mean to be like pessimistic or anything, but what is the point of this? Is this like applicable in
Yes, we're going to talk about a couple of specific types of series over the next few lessons that are applicable in different ways. For me, one of the coolest things about series is that they're patterns, and our world is full of patterns. So maybe not necessarily these number patterns, but our world is full of patterns, and math is a way to describe what we see.